Welcome back to the second half of this lecture, where I first will talk a little bit more about the hypotheses that explain how plate tectonics operates, and then a little bit about the different types of plate boundaries and how they manifest in Antarctica. So plate tectonics, we now believe, is driven by two mechanisms that are interlocked and related, and one is the hypothesis of ridge push and slab pull, and the other is the hypothesis of mantle convection. And there is still a lot that we don't understand about the interplay between these two mechanisms because so much of it occurs in the mantle or even relates to processes that we believe are driven by what's happening in Earth's core, and we cannot directly observe what's going on there. Ridge push refers to the mid-ocean ridges that we learned about when we learned about the discovery of spreading centers. And the spreading centers produce lava that solidifies into rock. And as the plates move apart from each other, that rock is going to get older and it's going to cool over time. It's going to get colder and denser the farther you get away from the spreading center that it originated in. And the colder, denser rock actually physically sinks more into the asthenosphere. Remember, the asthenosphere is the plasticky solid layer that the lithosphere, that is the plates, sort of floats on top of. The plates float on top of the asthenosphere. And different bits of crust that have different thickness or weight actually sink more or less into the asthenosphere, and that's something we'll talk about in the context of the glaciers found above Antarctica. But the colder, older lithosphere that is farther from the spreading center actually physically sinks more into the asthenosphere. And that creates enough of a gradient for this to actually push the crust away from the ridge, since it is technically downhill. It is sinking less into the asthenosphere at the ridge itself and more into the asthenosphere the closer you are to the trench where the ocean crust is going to disappear. And so that creates a downhill gradient, and that creates a very gentle gravitational force that actually plays a role in perpetuating the cycle of plate tectonics. And this is actually one reason why the mid-ocean ridge isn't really much of a high volcano is because you have this process occurring constantly away from it. You have ridge push bringing crust away from it constantly. Now at the subduction trench, what happens is the process of slab pull. The plate that is going down in a trench is going to physically get heavier and denser as it sinks. And that is because the pressure transforms the minerals that are in the ocean crust into different minerals, metamorphic minerals that are actually denser. And when the plate is deeper in the trench, when you have the transformations happening and making the minerals into different denser minerals, that actually pulls the part of the plate that's behind it down with it. So not only is it being pushed out at the ridge, but it's also actually being pulled down by the force of the increased density of the plate at the subduction zone itself. And there is a lot that I don't really go into here about how this happens. There is a process known as slab rollback, for example, when the downgoing plate is believed to curve in slightly. And the rocks I was looking at in Antarctica, there's one hypothesis that they were caused by an upwelling in magma related to that. But one thing I want you to think about is what is driving this? You have slab pull and ridge push functioning to perpetuate the cycle, but what sort of drives it? And we've come up with a hypothesis that relates to convection within the mantle. And there are convection cells in the mantle just as you have convection in the atmosphere. And convection, remember, is a method of heat transfer in which heat is transferred through the medium. Hot air or water or magma rises, and then once it cools, it will sink. The substance will sink. And warm mantle material upwelling causes spreading centers like that underneath the Atlantic Ocean or like those surrounding Antarctica. While at subduction zones, you have colder mantle sinking deeper into the mantle. And it's a little more complicated than this, but you essentially have these convection cells underneath the plates causing the mantle to move and providing an energy source in a way to the cycle of slab pull and bridge push. And this diagram does a nice job of showing how they interlock, how you can kind of think of the mantle convection as being like the gears that move everything along. And some of this is still not that well understood. Our understanding of what's going on in the mantle comes from using seismic waves to observe what's going down there, as well as studying the very rare cases where mantle rocks have been exposed at the surface to get a sense of what their chemistry and texture tells us about what's going down there. It doesn't tell us a lot, but it tells us enough to at least come up with a hypothesis, an idea of what is going down there, even if we can't directly observe it ourselves. Now, subduction is an event that occurs at one type of plate boundary. Seafloor spreading is an event that occurs at another. And we're now going to talk about the different types of plate boundaries that we find. Subduction zones are found at convergent plate boundaries, and seafloor spreading occurs at divergent plate boundaries. There is also a third that is usually seen accompanying seafloor spreading. And I want you to look at the arrows in this diagram. You have boundaries between different plates where you have arrows that are either shown in direct opposite directions or approaching each other, or in a single case, you have the arrows pointing sort of parallel and in opposite directions to the plate boundary. And that one occurrence in California is one of a very rare example of a transform boundary occurring on land and over an extended area, as opposed to as just one of the small connector segments in the mid-ocean ridge. As it turns out, the segments that I pointed out in the first half of the lecture connecting the actual fissures are transform boundaries, a third type of plate boundary. And so divergent plate boundaries are relatively easy to understand, and they all take essentially the same form. You have a mid-ocean ridge where new mantle material is welling up, and it cools and solidifies into solid rock, and the plates move in opposite directions. You have some of the material ends up to the left of the spreading center, some of it ends up to the right of the spreading center, and the spreading center is the boundary between two plates. So this is the type of plate boundary that you find making up most of the Mid-Atlantic Ridge, as well as the boundary between the Pacific Plate and the Nazca Plate out in what's known as the East Pacific Rise. You also have this marking the plate boundary between the Antarctic Plate and a number of the other plates that carry continents that used to be attached to Antarctica, like the African Plate and the South American Plate. And divergent plate boundaries actually begin on land. The mantle upwelling will cause a spreading center to form and the oceanic crust to form on land. And the oceanic crust is denser and so sinks into the asthenosphere more than does continental crust. And as more oceanic crust wells up and displaces continental crust, you'll first have a rift valley forming where you have the continental crust on either side dropping down, and you'll have this low continental crust forming, and on either side of the Rift Valley, I misspoke actually. The continental crust is shoved up into gentle mountains, and we'll talk about how we can actually see that in Antarctica, on Antarctica being one side of a former Rift Valley. And once this drops down low enough, you will get an ocean filling in, and the ocean will, over time, separate the two continents as the spreading center pushes the continents farther apart. And the interesting thing is that this is happening in Africa today. The Great Rift Valley in Africa is where you have magma upwelling as oceanic crust, and you have the continents being shoved to either side. The ocean hasn't quite yet filled in, but once it drops down low enough, the ocean will indeed fill it with water. And it's not a coincidence that the African Great Lakes are along this Great Rift Valley. Even though there's not an ocean there yet, you still have water cooling down to a very low point. And originally, Antarctica was connected to other continents like South America and Africa, and what you saw in that diagram happened there. New oceanic crust displaced continental crust to either side. The oceanic crust was lower, and eventually the ocean flooded in. And Antarctica is now completely surrounded by spreading centers. The spreading centers have since created ocean between Antarctica and Australia, Antarctica and Africa, and Antarctica and South America. And on this diagram, you can figure out where the spreading centers are by looking where the stripe that is the most vivid red is, because that is where the youngest oceanic crust is. And remember that you have young oceanic crust, and then on either side of a spreading center, it's going to get older as you move away from the spreading center in either direction, and the pattern is going to be symmetrical. So you have this spreading center, a relatively new one actually, separating Australia and Antarctica. You have one that's a little bit obscured by ocean sediments that separates South America from Antarctica. And then there's another one here between Africa and Antarctica and the southern Indian Ocean. And I mentioned that you can actually see in Antarctica an example where the continental crust was shoved up on either side, and that created a low ridge of mountains. And the Transantarctic Mountains are actually one of the bits of continent that were shoved up to either side, one of the rift shoulders from a divergent boundary. And the Transantarctic Mountains are located facing equivalent shoved up rocks in southern South America, southern Australia, and southern Africa. The Transantarctic Mountains are not especially high mountains, and in general, mountains formed this way as rift shoulders aren't especially high up. They just are high up relative to the surrounding oceanic crust. And Antarctica, interestingly enough, is not right along a plate boundary today, at least its coastline is, because Antarctica saw geologic action in the form of earthquakes and volcanoes as rifting began, but millions of years later, the coastline is miles away from the spreading centers. The spreading centers have more or less stayed in the same place. They have just produced more and more oceanic crust on either side, and that has physically pushed the continents farther apart. And there is now a lot more ocean between Antarctica and the other continents than there was when these spreading centers first formed. And this means that we have to introduce another term. A margin is another way to say coastline in geology, and we identified two separate types of margins in geology. We have active margins where the coastline actually coincides with a plate boundary, and we have passive margins where the coastline is simply the continent that was formerly joined to another continent and that has since been pushed far, far, far from that other continent by seafloor spreading and the flooding of a new ocean. And active margins are locations such as the west coast of South America, where you have a subduction trench occurring very close offshore, and you have a chain of volcanoes in the Andes Mountains, and you have lots of earthquakes occurring there. The same is true of the west coast of North America, where you either have subduction zones like you do off the coast of British Columbia and in the Cascade Mountains, or you have a transform boundary on land like you do in California. Or Japan is an example of an active margin, as is the Mediterranean. Antarctica, the coast of Antarctica, is nowhere near a plate boundary. The plate boundary is out here in the ocean and marked by the earthquakes that are occurring there. But there aren't very many earthquakes in Antarctica. Antarctica experiences a very small number of earthquakes from the couple of eruptions that happen at hot spots, but you don't have a plate boundary right along the coast. And so Antarctica is very geologically quiet now. And I mentioned that the west coast of North America is an active margin where you have volcanoes and earthquakes, but you notice that there's no dots representing earthquakes or volcanoes on the east coast of North America. And what the east coast of North America and the coastline of Antarctica have in common is that they were once attached to other continents, but pushed apart by seafloor spreading. And you'll notice that the the north coast of Europe doesn't really have much in the way of tectonic of earthquakes or volcanoes today either, because there is not a plate boundary there either. Same is true with the east coast of South America and the west coast of Africa. And so the Antarctic and the eastern seaboard of the United States have very similar conditions. Something interesting about the two when you compare them, though, is that you get a slightly different shape to the coastline in Antarctica because of the presence of glaciers. For one thing, Antarctica, so this is a bathymetric profile, which shows the elevation of the undersea levels as you get farther and farther away from the actual shoreline. And in a place like New York, which is along the eastern seaboard of the US, and it's a passive margin, you have the continental shelf where the edge of the continent itself is flooded by the ocean. And then you have this continental slope, which is the transition from continental crust to oceanic crust, and it's largely made of sediments that have piled up over time. And those sediments have just been able to accumulate over time very undisturbed by earthquakes because there's very little tectonic activity. And you would think the same would be true of Antarctica. But it turns out that as you move away from the continental shelf, for one thing, it slopes upward a little bit. And then when you reach the continental slope, it is much, much steeper. It drops off very suddenly. And it turns out that glaciers play a large role in this in several different ways. For one thing, the glaciers actually cause more significant erosion of the surrounding ocean floor than does anything coming off of the eastern seaboard of the United States. Glaciers, as we'll find out later, are a very effective agent of erosion, of rock removal. And glacial erosion accomplishes what is known as foredeepening. And the other thing is that the glaciers cause Antarctica to sink more into the asthenosphere than would a continent that did not have any glaciers covering it. And you'll see this in the form that as you get out to the continental shelf, you'll notice that inland it's actually sunk down quite a bit, and that's from the weight of the glaciers. And as you move away from where the thick glaciers are, there's a little bit of rebound. The Earth is a little higher up, and that's part of what generates this steepness also. The edge of the continental shelf is a little bit elevated relative to its equivalent in the eastern seaboard of the United States. And isostasy is a concept that the lithosphere is floating on top of the asthenosphere, but different parts of the lithosphere are thicker than others. Continental crust is thicker than oceanic crust, and so it weighs down, it pushes down into the asthenosphere more. And where you have an area that's where the asthenosphere is pushed down more, there's another area where the asthenosphere is going to be rising up more to accommodate that. And it turns out in Antarctica, the added weight of the glaciers actually pushes the Antarctic crust down into the lithosphere, into the asthenosphere, excuse me, more than you would have even in the case of most other continents. The asthenosphere elsewhere rises up to accommodate this. In Antarctica itself, it's pushed down quite a bit. And it turns out that a lot of Antarctica is actually under sea level because of the weight of the overlying glaciers. If the glaciers in Antarctica melt, the extra weight from the glaciers will go away. And if this happens slowly, what will happen is that Antarctica will physically rise out of the asthenosphere. That weight will be gone, and the continent will no longer be pushing down into the asthenosphere as much because there won't be the extra weight of the ice. And it's really interesting to think that the presence of these large ice caps actually affects it geologically, affects how deeply the Antarctic plate sinks into the underlying asthenosphere. Now, to formally draw a difference between oceanic and continental crust, Chemically, they are quite different. Oceanic crust is going to be more rich in iron, and it is going to be darker or more mafic. It's going to be very thin, but also very dense. And it is so dense that it actually does physically sink into the asthenosphere a bit more, and that actually creates the basins in which ocean water floods. That happened in the oceans that now lie between South America and Africa, as well as the Southern Ocean that lies between Australia and Antarctica, and it will eventually happen in East Africa in what is now the Great Rift Valley. And in fact, you find oceanic crust in places like Death Valley, where rifting began but then stopped for whatever reason. Death Valley is a failed ocean, and that's why it's so low down. It just never was connected to a main ocean. It never allowed ocean water to flow in. And the density also allows oceanic crust to sink at subduction trenches. Now, the funny thing is that continental crust is largely made by the volcanic activity that is incited by oceanic crust sinking into subduction trenches. And it is thick and not very dense at all. It is much more rich in silica and much less rich in iron, and the term for that is felsic. And it is actually buoyant enough that it does not subduct. Once made, it can't really go anywhere, and over geologic time, actually the amount of continental crust on Earth has been slowly but steadily increasing. And so the oldest rock on Earth that we have is all continental. We have continental crust from billions of years ago, and we sometimes have fossils from that old, but the oldest unsubducted oceanic crust is only 200 million years old or so. And subduction is one thing that can happen at a convergent plate boundary. Convergent plate boundaries are a bit more complicated than divergent plate boundaries because divergent plate boundaries always produce oceanic crust on either side. But at convergent plate boundaries, where you have two plates approaching each other head on, what happens depends on the type of crust you have underneath the two plates. And in the first scenario shown here, you have subduction occurring where a plate composed of oceanic crust meets one composed of continental crust. Oceanic crust is always going to be more dense than continental crust, and so it's going to sink below it and create a subduction zone. If you have two plates composed of oceanic crust, you will get whichever one is denser sinking below the other. And that's in practice going to be whichever oceanic plate is older. And that's why you sometimes get subduction creates volcanoes. And on land, you'll get a chain of volcanoes near the coast, like you do in the Cascade Mountains or the Andes. If you have this happening with two oceanic plates, you'll get a new set of islands forming, like you have with Japan or with a number of the Indonesian islands, or closer to where we're working with some of the Subantarctic Islands. But if you get two continents, they crash more or less. Neither of the continental plates can go anywhere because continental crust doesn't subduct, and so it piles up higher and higher and thickens. It literally experiences what is known as crustal thickening, and this forms high mountains like the Himalaya. This is a process known as an orogeny, or a mountain building event, and these mountain building events usually first occur as oceanic crust first being subducted and generating volcanoes, and then once the ocean between the two continents is gone, you'll get continental collision occurring. And at a subduction zone, you'll have the trench itself where the plate is going down, and you'll have a chain of volcanoes forming behind it. You will also have pretty intense earthquakes because you have old oceanic crust crushing under the thick continental crust, and that builds tension up. An interesting thing to note is that, contrary to what you might expect, the convex side of the trench, or the bulge, actually faces the direction that the plate is coming from. And a good way to think about this is to think about what happens when you put a dent in a ping pong ball. Earth is spherical, so if you have a plate going down, it's going to create a curve whose bulgy side points towards where the plate was coming from, which feels kind of counterintuitive. But you'll notice that on maps like this, the arrows point in the direction that the downgoing plate is moving. So the Pacific plate is the one that's subducting. The Pacific plate is going to the west, as the arrows in this diagram point. It is going underneath the Philippine plate, and you'll notice that the Pacific plate is coming from the east. The bulge overall, not the arrows, but the bulge points towards the east, where the Pacific plate is coming from. In other words, if you can see a trench and you want to figure out what direction subduction is going, you'll want to see what direction the concave side of the curve is facing, or the inner side. And you can see on the concave side of the bulge, they have the arrows pointing towards the west. Subduction is going from the east to the west. And that's how you figure out which of the two oceanic plates is subducting if you have a situation where both of the plates involved are oceanic. And we have this in the Subantarctic Islands. We don't have any subduction arcs in Antarctica itself, but the Subantarctic Islands were produced at convergent plate boundaries between the Antarctic plate and the various microplates like the Scotia and the Sandwich plate that lie between it and the South American plate. And you can actually see the trench in this diagram. This dark zone is the trench, and the islands follow along this. You have a chain of volcanic islands being produced behind the trench. Because subduction, you see the bulge points to the east, and that tells you that the plate that is subducting is coming from the east and moving west. And that's producing the South Sandwich Islands here, as well as South Georgia Island and a number of the other subantarctic islands. And the other type of occurrence that happens at convergent boundaries is continental collision, which we don't have actively going on in Antarctica right now. We don't have any cases of continents colliding. And in fact, there's not a lot of examples of this going on right now. The best example is in the largest and most prominent example is in South Asia, where the Indian subcontinent is to this day colliding with the rest of Asia, with the Eurasian plate, and a large mountain chain is being built up as neither of the plates, which are both composed of continental crust, will subduct. You often get the world's highest mountains occurring where continental collision is occurring. Since neither continent will subduct, the crust really has nowhere to go but up. And you actually, as a result, end up with remnants of oceanic crust getting pushed that are from the ocean that was between the two continents. They actually get shoved up into the mountains, and you have, in some cases, ocean rock that has clam and fish fossils up in the Himalayas because of this. And in Antarctica, we had mountain building occurring millions of years ago, hundreds of millions of years ago, in fact. And what I was studying for my thesis was actually one of these events, an orogeny that occurred early on in Antarctica's history. And we will talk more about orogenies and the building of the Antarctic craton later in the course, next class. But you can see in this diagram that you have several bits of land that are shaded differently. And that's to show that they're hypothesized to have been little bits of crust that were on different plates, but as the plates approached one another, they were grafted onto Antarctica, essentially. And since they couldn't subduct, it built up mountains in the process. Now, you do have also evidence of subduction volcanism, because what usually happens, again, is that you have one continent and then another continent or fragments of continent, and there's an ocean between them. And the ocean will subduct, but then once you reach the continent, no more subduction happens, and you just get orogeny. You get mountain building and crustal thickening. The confusing thing about my field area is that my field area was within the Transantarctic Mountains, and the Transantarctic Mountains have nothing to do with the mountain building event that put my rocks there. The Transantarctic Mountain uplift actually just uplifted some of these rocks and exposed them better later on. And that's a microscale lesson of you having to be very careful with attributing the origin of geologic structures to individual events, because multiple events have happened on the same spot, and you have to learn what was produced by what. There were some rocks in my area that were also produced by volcanic eruptions that occurred several million years ago, as opposed to several hundreds of million years ago. And we had to be careful to not confuse those for each other. The final type of plate boundary is a transform boundary, and these usually occur as the connector segments of mid-ocean ridge spreading centers. Now, if you notice, the divergent boundaries are staggered, and they are actually connected by transform boundary segments. you'll notice that the crust moves side by side. You don't have any volcanism occurring. You don't have crust being created or being recycled. You just have crust moving in opposite directions. And the plates move past each other. The funny thing about the San Andreas Fault in California, the one example of a transform fault that we really have on land, is that it does actually connect two separated mid-ocean ridge segments, just two very far apart ones, one in the Pacific Northwest and one in the Gulf of California in Mexico. And the thing you have to remember about mid-ocean ridges is that a plate boundary has to involve something different happening across either side of it. At the divergent plate boundaries, you have crust being formed and moving in opposite directions. Along the transform boundaries, you have bits of crust on different plates sliding past each other. But as you get farther and farther away from the spreading centers, you'll notice that the crust simply kind of just moves in lockstep. It looks like there's not really anything happening here. It's just a crack. And something that takes a little bit of time to get used to is that you have these areas known as fracture zones that are farther out from the spreading centers themselves. The interesting thing is that the length of these transformed segments will change over geologic time. Sometimes they will get farther apart, and it's largely to avoid an energy. It's largely to avoid an energy buildup in a way. It's a way to separate depending on mantle convection and what's going on down there, the spreading segments will get either farther apart or closer together. And so it's possible for these fracture zones to be reactivated if these spreading centers get farther apart. But presently, this is just crust that has been cracked open, and it's now moving in the same direction, so it's no longer considered to be a plate boundary. It's basically a dead fault. And you can see this in the mid-ocean ridges, where you'll have just these cracks in the ocean floor across where you don't have movement up and down, you don't have movement in opposite directions, you just have a crack that is from where a transform boundary broke the crust previously, fractured it, but it's not really moving in opposite directions anymore. And in Antarctica, you can see this in the spreading centers. You can see you have spreading center segments, and then you have transform boundaries separating them. You'll notice that below this one, you have the crust moving to the east, and above this one, you have it moving to the west. And then here, where you have the transform segment kind of go perpendicular down into the spreading center, you'll notice that there is still evidence of a crack going out in the same direction where the transform fault was. But you'll see that on either side of this fracture zone, below it, the crust is moving to the west, and above it, the crust is also moving to the west. The transform boundary itself only really exists in this connector segment. If the crust on one side of it is moving in the opposite direction as the crust on the other side of it, then it's a transform fault. But if the crust on one side is moving in the same compass direction as the crust on the other side, that is a fracture zone. We also have hotspots, where you have volcanoes occurring nowhere near a plate boundary. And hotspots are one of the very few geologic processes not directly linked to plate tectonics, although likely they are related. Some people hypothesize that spreading centers actually start as hotspots, and that some simply fail or simply stay hotspots rather than turning into a whole new rift. And yes, new rifts develop, and plates don't stay the same forever. I mentioned before that Death Valley was kind of a failed rift, and we have some examples where we get mantle upwelling as a hotspot, and it just stays that way. It doesn't develop a new plate boundary. So what is happening is that an uprising plume of mantle material penetrates the crust and generates a volcano. It generates melting. The plume will eject magma at more or less the same spot over millions of years, but the plates will continue to move on top of it, and the hotspot will be popping out magma in one spot while the plate will carry the older volcanoes away from it. And that's why you sometimes get a chain of islands where you have one active volcano, and then you have smaller islands that also have volcanoes, but those volcanoes aren't erupting anymore behind it. And that's what's going on in Hawaii right now. There's a mantle plume hypothesized to be erupting beneath the Big Island and feeding the volcanoes on the Big Island. And the Pacific plate is slowly moving away from this hotspot. The Pacific plate is moving to the west, but the hotspot is staying in the same place. And the hotspot carries these older volcanic vents away from the hotspot, and they get smaller and more broken down because you have ocean erosion breaking them down, but you don't have new volcanism feeding them. And so we have this also in Yellowstone because the Yellowstone hotspot is currently located below Yellowstone National Park, but the North Atlantic Plate has moved, and at one point the hotspot was actually below what is now Oregon and Washington. And the Columbia River basalts, which are these large lava flows that cover large portions of those two states, are actually this flood basalt that you get when a hotspot first forms, when the plume first reaches the surface and you get a big outpouring of basalt. And you get the Columbia River basalts from that, and then there's a trail of volcanoes that extends from the Columbia River to what is now Yellowstone that can be tracked with how the North American plate has moved over that time, which is pretty cool. In Antarctica, we have a couple of hotspots, and those are the only examples of volcanoes we have on the Antarctic continent today. The most famous is Mount Erebus, where a plume has generated a chain of volcanoes that is presently centered at Mount Erebus itself. And something to keep in mind is that the Erebus volcano is it's a completely different, it's not a plate boundary. It doesn't mean that we have an active margin. It's actually very far from a plate boundary, but there just happens to be a plume bringing magma to the surface on Mount Erebus on Ross Island. And you also have some hot spots on the Subantarctic Islands. On Deception Island, you actually have some hot springs that, like those at Yellowstone, are created by the heat of the underlying magma from the hotspot. And that is the overview of Antarctic geology. Next week, we'll learn a little more about how we got here and use our knowledge of plate tectonics to talk more about the geologic history of Antarctica. So look forward to lecture 6. Remember that neither lecture 5 nor lecture 6 is on the quiz, lecture quiz 1, and I will see you all soon.